This is the first. And Colin's going to get his stuff ready to go while I'm talking about this. For those of you who may not be aware, we are either sitting in or you're connecting to Canada's only synchrotron research facility, which is situated in the middle-ish area of Treaty 6 territory, also traditional homeland of the Métis, and currently known as Saskatoon in Saskatchewan. My name is Tracy Walker, and I'm the Education Programs Lead at the CLS. Before we get started, there's a couple of things that I would like to discuss with you, mostly logistical tips for this online environment if you're not used to this particular platform. One, I want to let you know or remind you if you weren't sure about it, we are recording this so that people who can't join us here today can kind of still participate and benefit from the story that Colin is going to tell at a later date. So please feel free to use the chat function if you're not comfortable with having your camera on, and that's perfectly good. There's a couple of different viewing arrangements that you can use. If you click on the at the bottom of your screen, when you move your mouse, there'll be 3 dots on the right-hand side. And if you click on that, at the top, you'll see a change layout button. And that can give you a selection between sidebar, spotlight, and tiled. If you leave it on spotlight, then whoever is talking or the presentation will be all that you see. If you use sidebar, you will be able to see the presentation and then also some of the video on the side. And if you use tiled, that will also, you will see the presentation and as many of the people as can fit on the side. So if you would like to be able to see Colin while he's presenting so that you can see him point to things, that would, I recommend one of those settings. I remind you to please keep your microphone on mute while Colin is talking so that we can kind of cut out the background noise. Now, that being said, questions are welcomed throughout the presentation. So if you would like to ask a question, then you're welcome to unmute yourself and let Colin know that you'd like to ask a question, or you can pose your question in the chat and either Amanda or myself or Anna Maria will pose that question to Colin on your behalf. Okay. Does anyone have any questions about the logistics so far? I'm watching it. You're working with it, Colin? Okay. Yeah. So then I'll move right into introducing Dr. Colin Laroque is a professor at the University of Saskatchewan in both soil sciences and the School of Environment and Sustainability, in addition to being director of the Mistik Askiwin Dendrochronology Lab. And I hope I pronounced that correctly.
Very good.
So the MAD Lab does dendrochronology, which is the study of trees, and in particular the rings of those trees, in order to gather information, the stories that those trees have to tell, whether that's environmental impact or a history of what things have happened in that area. There's a lot of information there if you know how to get at it. For the last few years, he has been adding synchrotron techniques as a tool to try and listen to these stories that the trees tell. And he's been working in particular with our education programs with high school student projects and university student projects and our new tree program, the partnership between that lab and ours. And so today he's going to talk to you about his experiences and the rings and the trees and the stories and a number of different things. And I'm very excited that he is the person kicking off this seminar series because it really shows the nature of the relationship between his lab and ours. I think it's really strong and very collaborative. So with that, I'm going to turn things over to Colin.
Thank you, Tracy. Can you hear me? Thumbs up, anybody? It all sounds good? Okay, wonderful. I too am really happy to come and be a speaker, specifically because Tracy said it was all expenses paid. So everything is on Tracy. So I even took a limo from my bedroom this morning to my office downstairs, and I ordered room service, everything. So it's going to be a heck of a bill. But Tracy's
Great. The check is in the mail.
Yeah, Tracy's paying. So what I'm here today to talk about is something I love is my trees and the tree rings that they have, but also at the same time, the interactions, as Tracy said, of our two labs and the rings of, when you talk about rings at a synchrotron, very different types of rings, but how the two of them are really intersecting and how they've intersected through time. And I'm going to start my story out really quite far back in time. And this is actually me at my brother's birthday. This is my back right here in the bottom corner. And my brother's birthday, this is a long time ago. I'm with all my uncles, my grandpa at the family farm, and my dads are off to my right here. And, you know, ever since I can remember, these are some of my first memories ever. I've always been at the farm. I've always been outdoors. I've always been, you know, following in the footsteps of my dad, my grandparents, my uncles, my aunts, hunting, fishing, doing chores, riding a horse, whatever it was. I was always enjoyed that. And I was that kid who would come in frozen, warm up, and then go right back out again. And being outside was that really special time for me. I guess this is pre-internet, you know, everything. And so we had lots of fun, but it was all outside almost all the time. And as I progressed through my, you know, high school and my moody teenage years, and then I went off and I eventually started doing university and knowing what I wanted to maybe do more with my education, I could read a nice textbook, but I much more enjoyed being outside. You know, here I am in my master's degree. Most of my early research, you know, probably involved a mountain landscape somewhere. I was out in Alberta, BC, wherever it was, doing some kind of thing, asking questions about what I was interested again outside. And that's really where I was comfortable, and that's where I spent almost all my time in my education years as well. Eventually, I got my master's and my PhD, and I went on and I got my first job teaching. And although sitting in a lecture hall is fun for some people, I really enjoyed this kind of teaching where a student had a question about something like a beach. Here we are in New Brunswick, and I was out in the East Coast at Mount Allison University, and you know, really started developing a lot of my courses to take the students outside, take them to where it's really an interesting environment, something that's very different for them. Maybe take a prairie kid out to a beach, or take a maritimer out into the mountains or something like that. And so I worked on this a lot, and I spent a lot of my time trying to do this hands-on teaching, putting something in their hands and working its way through. And even that, you know, right down to my very intro classes. If it was raining outside, well, we're going outside, we're going to get wet. But there's always something interesting to see. And even in this case, you know, although some people might get freaked out about a spider or a spider web, you know, some of these students, the big smiles on their face, that love of being outside, being in the element. Yeah, your homework's getting wet, but boy, that was fun. And a really interesting learning environment. And that's really where I think the people who are interested in the same subjects I am in environmental science, they love to be outside. You can teach it from a textbook, but being outside puts more smiles on their face. And that's actually where they come up with some of the better questions. And I think more learning gets done. It even got so much that I would take all these maritime kids, so people from New Brunswick, Nova Scotia, you know, even Quebec, Ontario, and I would take them out to a field course, 10 days in Jasper, and this is Mount Saskatchewan and Saskatchewan glaciers. So this is kind of the North Saskatchewan rivers. That's where it starts. And here we have a group of students that I would take out, and the one requirement that I had for them is that they could never have been to Alberta before. And it was easy. I'd get 40 or 50 applicants for 15 or 16 spots. And everybody would pay the flights, everybody would pay to come out, because that challenge them, bringing them to a brand new environment, almost like a brand new textbook, and putting them in that textbook and having almost no kind of strict guidelines. We just say, what would you like to see? You know, oh, I'd like to go see a glacier. I've never seen one. Well, let's go here, Parker's Ridge. We can look over and see one of my favorite glaciers. And we would walk out and I want to touch the ice. Well, let's go. We'll walk out and go and see it. And as I answered their questions by opening that textbook any direction they wanted to go, I really kind of fell in love and saw all the benefits of this inquiry-based learning, letting that light turn on in their heads and following them and backing them up and seeing what they want to learn and just backing them up and taking them there. And if I didn't know what the answer was, I would say, I don't know what the answer is, but we can find out together and we can learn together, because when you get out into the real world, there's all kinds of things that you've never seen. Well, what I did for a research, of course, is it's dendrochronology, as Tracy said, or using tree rings to provide environmental information. Those trees that wherever they're growing, especially in Canada, they grow and they put on a ring every year. And in each of those rings, it tells something about what the environment, wherever that tree was growing. And one of the things that we don't do well in science is actually have a long-term perspective on things. And that's where a tree that's maybe 200 or 300 years old, growing in one site, has seen that site change for 200 or 300 years. And they've seen the dry times, they've seen the wet times, they've seen when the chemicals have changed in their atmosphere. And they tend to incorporate all of that into their tree rings or into their physiology somehow. And these are the kinds of questions that I like to unravel by, in essence, talking to the trees and asking them, what have you seen when you were sitting here in this site? Common things that I tend to look at were dendroclimatology. You're using trees to look at past climates. What was the climates like for those trees in that location? Or dendroarchaeology is an example where we can go in and even though there's some archaeological structure, we can go in and we can say, well, when were those timbers cut down? And when was it used for construction? And what happens? And just giving some information will help people who are investigating something understand that. A good example of this is that we work closely with a TV show, The Curse of Oak Island. And they find timbers in these wells and bogs and wherever, and they don't know anything about it. And specifically, they don't know what time frame they come from. So they'll send us the samples and we can kind of try to figure out where they come from in time. And then depending on whatever they're looking at, they get a good example of saying, oh, maybe this was such and such looking for their treasure back in time. And so we can use the time aspects of the trees again to answer some of these questions. And the last thing, and something that probably pertains most, is dendrochemistry. Those trees are incorporating all of the soil nutrients and the atmospheric conditions to grow. And in that, they're also including a lot of different chemical reactions and chemistry in the soils, and they're incorporating into their trees. And this, again, some really interesting questions can be devised around that, and often the trees can help talk about the environment and tell us. It's very common, and wherever you go in Canada, to have some of these old mine sites or old sources of pollution that have been started way back when, before there was something called an environmental impact assessment. They just started mining and then they polluted. But nowadays it's easy to say, well, it's always been like this. There's always been, let's say, lead in the atmosphere, lead in the soil. And it wasn't us who did it. But the trees can often tell you that, because the trees were growing before they started mining. And then they maybe come along and say, oh, this is when they started mining, and they have a timeline of what the environment was like and how it changed. Well, how I read the rings, it really depends on what the question is, but usually we'll look at the annual ring, or that whole kind of band from light to dark is an annual ring. Or sometimes we can break up that annual ring of the growing season into two components: an early wood component that's growing earlier in the season, so that's usually your spring growth, and then the late wood, or sometimes the later in the summer when the tree starts to finish off its growth and get ready for winter. And we've all either seen around a fire ring or seen a stump and counted the rings. And each year of that tree's growth, it puts down an annual ring, and you can kind of see its kind of the history and the storyline within that. And that's basically what we do. To collect these cores, we don't actually, it's not like firewood where we cut down a tree, but in some cases, like let's say if a glacier ran over a tree, or if someone else cut down a tree and made a timber framed house with it or something, we can see the whole disc, but we try not to hurt the trees. And how we collect samples is we have what's called an increment core, these blue handled things that Emily's using here, and we slowly auger them into the tree. And what we do is we pull out a small pencil, sort of the size of a pencil, sample of that tree, and we know all the rings going into it. And it's kind of like if you went to a doctor's office and punctured, they took a needle of your blood. We do puncture the skin of the tree, but the tree has a mechanism just like you do to quickly heal over, and it doesn't really harm the tree. So the harming is minimal. We don't have to hurt the tree, but yet all that information that the tree has, we can collect in one of these tree cores. And then we pull out or extract the core with an extractor spoon, and we generally save them. We put them in a straw, tape them, label them, and bring them back to our laboratory so we can process them and really get a good feel for what the story is for each of those trees. When we go back into the lab, we come back with all of our bundles of cores or our individual cores and our labels, and they have all told us something, trying to answer the questions about what happened at that site. And here we have in question number 2 here, Jeff, he's taking out the samples that we brought in from the field out of the straws, and we lay them down into like a grooved slotted mounting board. We transfer any labels or any information that we need on there, and then we glue them in with just some carpenter's glue. It looks like all mustard containers there, but that's just some glue that we put in there because we like the nice fine tip of the mustard containers, and they go into the slots well, and then we can glue the cores in. And the next step is that we go back into sanding rooms, and we sand them flat on different various sandpapers, and we go from very coarse sandpaper to finer and finer and finer. And in some cases, like in number 2, we even take a buffing wheel, like a woodworker might use, and we buff out all of the dust, and we polish up the wood just like a tabletop surface so that we can see each of the rings and, in fact, all the cells inside the rings. Because even individual cells can tell us things about what's happening in the environment when that tree was growing in that exact year or part of that season. And once we can see everything really nice and fine, then we go back into our computer systems, and we either put them under a microscope and we move along a moving table. And our lab work is we measure these rings. We measure from one boundary to the next boundary across. And we usually do that in 1/1000th of a millimeter. So it's underneath the microscope, high resolution. And kind of like you see in the back of the screen, we blow up the rings under the microscope, and we very precisely measure from one ring to the next ring. And when we do that, we save all the measurements, and we assign years for them. We know what year we took the sample. So let's say we took it in the summer of 2020. Well, that's the outside of the bark, and then we start counting backwards, and we go one ring back as 2019, 2018, 2017, and we keep working our way back as old as the tree is. We have other systems too in place. So for example, we have what's called a Dendro system. So you can scan in cookies or cores, in this case, or disks, and then put them on a computer monitor, tell the computer start here, measure from here to here. And again, this is Zach working on a wind project. We were trying to see if the wind in these exposed areas changed the shape of the rings from one side of the tree to the other. And you can kind of see that in this disc, but it also shows our Dendro system and how we're able to, again, measure and count the rings, assign the annual boundaries, and we can, again, do that to 1/1000th of a millimeter. So very precise measurements about getting how wide the trees were and how did they grow in each individual year. And then what we do with this is we create more or less maps, or we go into this, kind of a spreadsheet world, and we start to play with the data, the measurement data. And I'll explain this to you for a second here. This is just a whole bunch of white spruce up and down all the spaghetti. Each line represents the growing pattern, that wide, narrow sort of millimeters of growth through time. And that's all the spaghetti lines on here. And then we have a timeline on here, again, going back from, in this case, 2012, all the way back as far back as the trees were. And then in here, I kind of put some blue lines and some red lines. So some blue lines are where it's relatively wide, and the rings are relatively wide, and you can see they're wider here. And then the red is years where it was really poor growth, very narrow growth. And all of the trees really show that, and they all have a narrowing. And you can see that in those little tiny rings that we have here. And you can go the wide and the blue and the very narrows here in these certain sections. And so even with all these trees from the different environments in this region, you put them all together and they're telling one more or less story. And so we can average that down, and we get what is kind of a picture of what's happening in the growing environment. In this case, all these narrow parts of growth were droughts. The big drought we had in Saskatchewan, 1961, all of the trees show that kind of drought. Even if they were growing a bit better than their neighbors, they were showing the drought. The late 80s, the 1988 drought is there. The early 2000 droughts are there. All the trees are showing those kinds of things, and they all turn into asynchronous, and they're all kind of relying on that limiting factor of growth, which in this case is in Saskatchewan was some drought years. And we can do this for any environment that's out there. And we can go in, take multiple samples, and collapse those samples down. And then we end up with what we call a base chronology. And this one, it's, goes back 200-300 years old. One here is an average. So the center line is more like an average. Above one would be better than normal growth. Below average is worse than normal growth. So good growth, poor growth, one being the average. And you go back in time. And what this is more or less at that location for that species of trees, we get a fingerprint. This is how the group of the trees, the forest has been growing through time. We know when it was good years, we know when it was bad years. And that really shows us more or less a fingerprint of how things have been going and what maybe has been happening to their growth to change that fingerprint. What's making it getting better growth and what's making it get worse growth. And that's how we can go in and sort of answer some of our questions. Well, the first area I want to go into here is just an example of dendrochemistry. And really, this was the project that brought me to ultimately the Canadian light source. It was way back. I was in Mount Allison University, Sackville, New Brunswick. And a student of mine, Hannah, came to me and said, I want to study some tree ring stuff. What do you want me to do? And I said, I don't want you to do anything I want to do. I want you to do something you want to do. What interests you? And so what Hannah did is she went to this site. She was from Cape Breton, and she went to this site from the government of Canada. And then in here it said that these are all greenhouse gas emission, large facilities. These are some of our big, heavy polluters across Canada. And she goes, well, what's interesting to me? And she went home. She went to where she's from. And in this area, this is Cape Breton up in here, and this is like the Sydney area where she was near from. And there's a big red dot there. And that big red dot was signifying some pollution that was in her home area, and it was the Sydney steel plant. The Sydney steel plant made steel, obviously. They've been there since the 1920s. And most importantly is that to make the steel, they burnt Cape Breton coal. And Cape Breton coal happens to be some of the dirtiest coal we've ever had in Canada and anywhere can find. Lots of heavy arsenics, lots of lead, all these pollutants that came out. And there's many stories in Cape Breton and around Sydney that, you didn't put out your white laundry on the day that the wind was blowing off the Sydney steel plant towards your house, because your laundry would come back much dirtier than it went up. And so it was a really bad, and this is the Sydney steel plant was really what made what they call now the Sydney tar ponds. The the chemical soup that is kind of left over after this plant closed down in the 80s. It got so bad the federal government had to buy houses from the people because they were worthless. It's so toxic. Almost everybody on this one street across the street died from cancer. It's a really bad situation, a human health hazard. So it's all fenced off now, and they have to try to remediate it. But what we wanted to know was, did those trees in that area actually pick up any of these chemicals coming out of that Sydney steel plant? And that's what Hannah went off to try to figure it out. What Hannah found out is that there's this science kind of out there that if you can take an X-ray and you bombard a test sample with it to such a degree, off will bounce off signatures or like backscattered light that will tell us which direction and how, what frequency it comes off. Kind of gives you information about specific elements. So is it lots of iron coming off this sample? Is it chromium, nickel, arsenic, whatever you actually have on that? You just got to find an X-ray fluorescence machine. And no one really had done too much by sticking a sample in front of an X-ray of trees. So she said, well, could we take our trees and the timeline and see from a tree that was before the Sydney steel plant started and bombard it and see, oh, there was no, let's say, lead or arsenic in the sample. And then after it started, the lead and the arsenic started to come into the trees and the tree rings. And that was the big kind of goal of her thing. And so we went off and we went to the medical physics laboratory in Mount Allison, and there it was, our monster X-ray fluorescence machine. It was a little handheld unit. You could pull the trigger and it would shoot out a little X-ray beam. And we had a very small aperture. And so in the right-hand picture, Hannah would take a piece of core. We could only put in about 1 millimeter wide. So she'd take a piece of core. She kept them all in these pill containers, and we put in 1 millimeter by 1 millimeter, and we would zap them and see if some of these elements that we were interested in were coming out. It was fantastic. It worked so well. Hannah and I were so excited. Everything kind of worked. It was an undergraduate project, but boy, it was really neat because no one else had really tried that. And we both got to walk around the Sydney tar ponds, and we both got to do some really interesting science. And again, it's that experiential learning of going out and trying something that no one else has ever tried before. Even if we fail, it was so much fun. Well, this was about 2010, and about 3 years later, I got a job offer, and in January 2014, I came to the University of Saskatchewan. And I was told they had an X-ray fluorescence machine too, and so I went over to try to see it, and it ended up, here was me on my tour of the CLS. And the X-ray fluorescence machine went from a handheld unit that was, you know, a few centimeters high and millimeters wide, we could put a sample, to suddenly a facility that was the size of a football stadium. The rings of the inner and the outer rings of the synchrotron were, you couldn't yell across. It was such a big thing. And I took a first tour and I walked around on the observation deck looking down onto the synchrotron, and I said, I have no idea what that beast does, but they tell me there's an X-ray fluorescence machine in there, and so I want to somehow find out how to get in there. But I was new, and I was just starting to get into my classes at University of Saskatchewan, and so I went about my business, but I said, someday I'm going to go there to try to work. Well, little did I know that my someday would come to me on a telephone call. I was sitting at my desk one day having my lunch about noon, and a phone rang, and I put down my peanut butter sandwich, and then there was this squeaky little voice on the other side. It actually ended up being this guy, Alex, on the other side. And I said, hello, Colin. And it was just kind of silence for a few minutes. And then, hello, is anybody there? And then I heard, hey, do you know what increment core is? And, you know, there was no hello or anything. And I said, oh, this is kind of like a bad Bart Simpson joke or something. And I'm trying to think of, you know, okay, I don't know this joke, but I said, yeah, I do know what increment core. Who is this? And what's happening? He goes, well, my name's Alex, and I'm a student, and I'm from Luseland, Saskatchewan. And we have a science club, and we have some grade 9s. I think here's a little Kara here, grade 9, all the way up to some grade 12s in their science club. And we're interested in this place called the Crooked Bush, where these crooked aspen are growing really crazy and across the road. They're nice straight trees, but we really want to understand what's happening there. And someone told us that if we took an increment core, maybe we could go and put it in the CLS, the Canadian Light Source, and we could find out more about the chemistry of these trees. But what we don't have is an increment core, and we want to get one and try to understand how they work and see if we can take a small sample from these trees. We have an experiment, and the experiment is to try to measure what the chemistry of these crooked trees are, and then walk across the road and see if the chemistry of the straight trees is any different. Is there some kind of chemical difference between the two? And so I said, hey, I know where that bush is. I actually have many increment cores. I have no problem lending you guys some. Unfortunately, I couldn't go the day they were going to sample, but their teacher was going to come to the city that weekend. So I said, hey, I'll meet your teacher we met at a local Tim Hortons. He bought me a hot chocolate, and we discussed how to use the increment cores, and I gave him a bunch of supplies. And I told him my best, and I said, here, call me if you need me, but I'll have to be at work that day, but go out and take some samples. And if you get the samples and you need anything, call me back. And so they did. They went out and I actually got some samples. Here's the science club coming back. And on the day they were coming to Saskatoon to tour the CLS, I said, well, come a little early and come to my lab and we'll discuss what you have. And I'll tell you what we have and take some extra samples. We'll mount them and we'll process them in my lab. And so this high school group from Mooseland, Saskatchewan, basically came to my lab in the morning, and I explained everything I could to them, and they went through their processes of samples, and they figured out how old the trees were. They saw the rings, they aged them, all those kinds of things that they didn't have information on from before. But more importantly, they invited me along in the afternoon. So when they went off to the CLS in the afternoon to take the tour and get down onto the beam floor, areas that I had never gone, there I am kind of tucked in the back of the room, but I'm kind of listening attentively. And I got to meet, for example, David, the beamline scientist idea, and the whole thing. So I just kind of kept quiet and stayed in the back, but I really got to better introduction to see the kinds of process, and again, X-ray fluorescence that I could have used in the past, but on a totally different scale. And that was just so wonderful to me. A great learning experience. As that group went through, they asked me to mentor them, and I met, for example, Tracy and David, and they all had questions for me. Well, how do you normally mount trees in a synchrotron? And the answer was, no one knows. I can't find out. So we're going to have to try and do it ourselves. And so as the students went through, we used all kinds of mounting instruments, and we used all kinds of examples, and we started seeing chemical differences. And they were learning and going through their educational experience, but so was I. I was watching them. I was not doing any of their work, but I was excited. I wanted to be here. I kind of was, a kid in a candy store from a scientific perspective, because everything they found out about the soils, everything they found out about leaves, everything they found out about the trees were exactly what I was interested in too. As they learned how to run along and run the machines and do the sampling, I was able to look over their shoulders and talk to them and ask them questions and see what they were doing. As their results came back and they hung them on the wall, I was able to help interpret them and be taught by David and Tracy and everybody else who was from the CLS of what they actually meant and how that actually could go. And I helped direct ideas and thinking so that when the students altered their experiment, they were answering questions that I was just as interested in as they were. It really helped that there were some really smart kids in this group, because they really got it at a level. They were really excited by what they were doing too, because again, it was such a new experience running these trees through. At the end of their experience, they all passed and they got their diplomas more or less. But, they invited us along, and there I was in the background again. But more importantly, here was some of my graduate students. So my grad students kind of piggybacked on this science club too. And there's Magley. We'll talk to her about her in a second. And she ended up mentoring along many other groups. There's Jay. He mentored along other groups as we went through in time. And this one's Nicole. She was actually studying something right now that we were looking for an X-ray fluorescence machine someplace. And suddenly we saw the best one we have in Canada and we wanted to use it. Nicole was studying the oil sands region of Alberta around Fort McMurray. The trees there were getting really sick and we had no idea why. She had some sampling sites. You can see way over here on the left is a control site about 150 kilometers upwind, and the same kind of forest right across into the Fort McMurray site. So all these other different oil sands activities. And we had a site right against the gates almost. So site 0 kilometers and 50 kilometers away from the main Syncrude area. And what we were seeing in the trees, this is that one is average again and timeline across the bottom. But what we were seeing in the trees, the control, the 50 and the 0 kilometers were more or less the same story all the way through time. And the oil sands started roughly in 69. So even through the 80s, everything was going along pretty well. And then they really had some big upgraders around the year 2000. And just after that, in about 2003, 2004, these signals really started to diverge. The control kept around 1, and the 50 kilometers went down, and the 0 kilometers went really far down. It had some really poor years. And you can actually see this. I'll zoom into this time period in the cores. Again, same 60-year-old tree cores, sites from 0 kilometers, 50 kilometers in control site. And if you look at that same area, the rings in the control are very, very tight, are very wide getting to narrow. And then in that 0 kilometers, really, really tight rings. The trees were just doing very, very poorly and they were getting quite sick. Here you zoom in and you can just get on the exact same scale, you can kind of get a feel for on the control, how much more biomass it was putting on and how few rings were kind of incorporating into that at the 0 kilometer site. At that 0 kilometer sites, all the needles on the trees were turning brown. They were falling off. The trees were dying in the understory. And it was turning into like a scenario where it was just ripe for a forest fire. And a few years later, that's when that Fort McMurray fire came and really just wiped out all the forest because the forest was so sick and dry. It was a really it was a site ready to be burned because of the dead trees. Anyways, what Nicole did is she came to our agroforestry lab and she ground up all these soil samples. We took samples of the trees, the needles, the leaves. We took aspen and we took conifers, white spruce. We ground up all the needles and the branches and the roots. We did soil samples from the surface layer from 5 centimeters down, 15, 20, all the way down 50 centimeters down. We dug soil pits and took out that so we could see all the components. We ground them all up, and here you can see the different kind of components from maybe the green leaves to the different soils, to roots, to wood, to branches, and we wanted to test them all. What we did is we went back to the CLS and they had a pellet press. So we weighed out all the same amount of sample in these trays. We put it into this press collar. We pressed it down with a few tons of pressure, held it there for a while, and then out pops these little pellets. So we took that material and pressed them into a pellet. And that pellet is kind of an amalgamation of that series, whatever it happened to be, a root, a leaves. And we made all these pellets, and in the soil samples, we put them in standard holders of different depths of soils, and we put those in so we could look at them too in the CLS. And then just like those students taught us, we put them, in this case, a little bit different. We put the pellets into a vacuum chamber, and then we looked at them on XRF, and you can see over here on the left where you can align things up, and we bombarded it with X-rays, got the fluorescence and saw what kind of chemicals were inside each of our tree parts. And here's something from Nicole, one of her big findings. If you haven't seen this before, this is more or less just a picture of an energy level and then a number of counts or intensity. And what it's doing is it's showing you these squiggly lines, and we have leaves from the control site and leaves from the zero site. And these peaks represent, individual chemicals. So when you see this Jarge peak here, you'll see calcium. This peak is iron. This peak is nickel. And in general, the lines were very much the same. You can still see this. The red and the blue lines are the same. But what was very different is that at the 0 kilometer site, right on the kind of ground zero, there was huge spikes of manganese. And manganese is one of those elements that you need to grow a tree anytime you do photosynthesis. But you need that manganese. But if you get too much manganese, you can poison the tree. And this is what we believe. We're turning all the leaves brown and all the needles, to making them fall off when they're really close. And manganese is one of the things that was coming out of the stacks at the Suncor plant. So in that valley, it was just being bombarded with the pollutants. And that's what we believe was trying to kill the trees, this really high amounts of manganese. And it was especially hitting the conifers, because the conifers the white spruce would save its needles for 4 or 5 years. Whereas something like the aspen trees would grow a leaf, all the manganese would go to the leaf, but it would fall off in the fall, and then it wouldn't poison itself. And so it was affecting all the conifers in the area. And again, that was kind of the main finding of her study. But it was fantastic for me as a director, because now we've met some of these people, we've met some of the things. And so I put in some experiments that I wanted to do on my own. I was still looking at lead in St. John's, Newfoundland. That's where the most lead is in children, in their hair, and the most sickness that we have in lead in Canada, in St. John's, Newfoundland. And so I wanted to study that. And so we had some tree cores, and I applied for some beam time. We got some beam time on Vespers. And through the night, we had shifts through the night. And so I needed some volunteers to help me. And so I asked some of my students to volunteer, and I had so many hands put up, because they were all excited to come and do the same thing I was, learning at the synchrotron. It's such a beast of a machine. What could we do? And there's microscopes here and everything, and wires, and I don't know what all these gizmos are, but if you teach me what to do, I'll do my best. And here's an example of a young Zach who's going to be a speaker coming up, and Jessica and Ben. A lot of these people I work with further, but they all volunteered that first time. They barely knew me, and they all volunteered to come and work at the synchrotron. 2 o'clock in the morning, here they are, laughing, having fun, smiling, and doing science, right? And to me, that's the ultimate way. Anytime you're having that much fun, suddenly, something like math or physics or something like that gets thrown out, and it just becomes such a fun thing, and you want to learn, that you end up spending all your time and your energy wanting to learn all that science behind it. And I love that. And that's kind of one of those things that really struck me. In my day job, I was also teaching classes. And so I would be teaching environmental science 110. So intro 110, you come out of high school and the first kind of class you have. And I said, boy, Tracy, as an education, I would love to be able to take my first year undergraduate students walking out of a high school from wherever they come into my class. And within a few days, I bring them into that CLS. We do almost what you do in your education team, but instead of being a first year research experience and going to do my regular labs, which are indoors, or even some are outdoors, but kind of boring, I'd love to take them to the synchrotron. And so that summer we developed a pilot and a fire on the beam lines. So that first year research experience, but some people will get to go to the beam lines. It ended up being 12 students that we commissioned and we got permission for. And we said we might not even have 12, or else we're going to have more than 12. If we get more than 12, we'll put our names in a hat and we'll draw the lucky 12 students, and they'll come to the synchrotron, and they'll do what some kind of experiment at the synchrotron, and it'll be fun and exciting, and maybe we can turn them on to science. And that's exactly what we did. We learned a lot, but we also have been doing it continuously since that time. One of the very first stories I have, though, is that very first year, the beamline went down right when the students were supposed to finally get their time. This is right at the end of November, beginning of December, classes are over, So they're finally worked all term long to get their experiment in place. And I said, we lost our beamline. We don't have any time anymore, and the class will be over before you actually get a chance to go in. So I can give you a mark now. Who wants their mark now and not go to the synchrotron? No one put up their hand. And then I said, well, who cares about the mark anymore? Let's just get into the synchrotron, even if it's January or February, so you can run your experiment. Will you wait? And they all put up their hand. And I was so blown away, I took a picture. So here it is. They all said, yes, we want to run that experiment. It doesn't really matter when you can get us in there. We were lucky. They actually wrote their final test, and a couple of days later, it was on a Saturday morning, the beam came back up, and David was able to take them through. Tracy was able to get us in. We didn't have our full shift, but we had a few hours, and that was enough for them to run and drive the synchrotron, and they were so excited to get in there, and so was I. And again, they did phenomenal in the kinds of science they did, but they learned so much. Most importantly is that they got to drive, and everything that they worked with, and here's Rihanna putting in their samples in the beamline, everything they wanted to, even if it was just for a 1-3 minute zap, they got to run it, and they got to see if their question was answered, yes or no, or like most times, more questions came up than answers, and that's exactly usually what happens in these kind of scenarios. Each of them got a chance to run it. They made sure that everybody got their hands on, everybody got to load up samples, everybody got to sit at the computer and hit go and watch their samples come in. And that one, again, later on talking to these people, and here's Brooke, who later became one of my master's students again, they all said, yes, we want to run it, and that was very important to do that. They each had a chance to actually ask and alter their experiment, and as the results came in, there was enough room and enough time for them to kind of alter their experiment depending on what was coming in, and they really dove into it and got a chance to think through their problems and think through their environmental issues. That project and that kind of pilot really took off in the sense that there's other classes doing that now, and this is an example of one of Tracy's education curricular classes, or an edkerr class. And we're no longer in the point where we're just at the synchrotron or just in my tree rig lab. Wherever these students think up some crazy idea, we bring them in. You know, here these students are edkerr students. I think one was wants to be a phys ed teacher, one a grade 4 teacher, you know, another a music teacher. It doesn't really matter, but they want to teach, and it's that process of learning and teaching themselves, and that inquiry-based learning that they're getting in here. And when they come up with some crazy idea, we on our part, my lab and my students, we do our best to make sure that we can help them out. In this case, what they wanted to do is soak a tree core in acetone to boil out more or less the sap, to see if the sap has some chemicals that are different from in the wood to come out. We've never really done this before, and there was no manual on how to do this for a synchrotron. And so we made one up, and we tried it, and we figured it out. And these ladies in this case went through and did their best and processed everything in a soil chemistry lab, and then took it to the synchrotron to test the wood and test the residue left over, the liquid left over. Here's some more edkerr, I think, students that we came in, and, you know, getting them out of their education and getting them out of the synchrotron, but bringing them into my lab and getting them to stick their faces in a microscope and seeing what they're doing and aging a tree and finding out elements of their question and letting them do it. You know, this is on a Sunday morning or a Sunday afternoon, and they're in there and they're all kind of watching what they're doing and trying to see if they can each do it, and then, you know, get out of the way, fighting to get their face in the microscope. That's an exciting aspect, and for me, it's such a well worth, you know, Sunday afternoon volunteer time to come in and watch the excitement on their faces as they go ahead and learn whatever they feel like learning, and we just back them up. We've seen this again later when a couple of years later when the synchrotron's electron gun went down, and every beamline was down except one. The mid-IR had their own mid-IR source, and so we asked, you know, could we bring some students over for one part of one shift, a shift, 4, 5, 6 hours. They make some time for us, and then the students delve into their samples, trying to figure out how they can use the equipment there. What does the equipment do? Ask a very simple question. In this case, these groups just try to figure out, could they use a mid-IR, get a mid-IR image off of various thicknesses of wood if they used cutters to make various thicknesses of wood, and could you get good imagery from very 5-micron thick images? And they were able to do that, but the processes and the fancy equipment that they get to use, they'll never remember the names again maybe, but they'll remember what they did. And by far in my evaluations, these are the most fun things that they did in any parts of the class. Maybe that says something about my teaching, but at the same time, I think they get so much from this kind of learning. And I think this is just it. This is the ultimate. They either go back to the synchrotron and do a public presentation, or in my class, at least, we go off and do poster presentations. And here we are, where everybody's kind of scared, and there's some judging panels, some judges coming by to ask my students, and here are the students, and they did a synchrotron project, and there's Magali, their research coach, in the background, not saying anything, but kind of looking over the shoulder. And each element, that aspect that Magali would get from teaching was so special, and she just loves it. And there's something that those students get, the judges will come back and tell you, like, they know their project so much more. They created every graph, they got every number, they put it on there. They had questions of why they got that number, how they put it on there. And then the judges will go to someone else who did maybe more of a literature search, and they'll say, well, where did you get that graph? Well, that graph is by someone else. How did they make it? I don't know. I didn't make it. I just got it from my research. And so the kind of education and the kind of confidence that we can give these students as we bring them through is just remarkable for me. And here we are in this public poster presentations, and my synchrotron students are excited to finally get to share their work, versus the other ones are just worried about they'll ask them something that they don't know. And so it's a really challenging but rewarding to see this. And I wish I could bring every one of my students through, but at the same point in time, I'm just so happy and that I can make that partnership with the CLS to bring on that sort of science training to those few individuals, usually 10 to 12 a year, but we give them something that they remember on all the way through the rest of their career. Well, that's more or less the end of my talk. They said to keep it to that time period, and so there I am. But if there's any time left over, I'd love to answer any questions that anybody might have. So if you have questions, please bring them on.
Well, thank you very much for that, Colin. And then now we get to see ourselves. And I want to thank everybody for spending your time with us today. Does anyone have any questions that you want to ask?
Crickets, lunchtime.
So quiet. Okay, well, I've got one for you, Colin.
Oh, Jesse's coming, yeah.
Okay. Jesse or David? David, do you have a question?
Jesse was coming. Is there any way you can...
Oh.
Is there any way that dendrochronology can be used to help predict things and or study impacts currently happening? Or is there primarily a historical approach due to the nature of the tree ring growth? We can go into the future. As I talked about a little bit in the dendroclimatology, mostly in certain scenarios, like think through droughts, the things that are growing the trees are climate related. And some of our best and brightest minds in the world are starting to create climate models that go into the future. And so we've been able to do mathematical relationships between tree rings and climate in the past. And now we have these predictions of future climates. And so what we can do is we take that future climate data and said, based on what we know the trees have grown in the past, if you give them this much temperature and this much moisture, they'll grow this well. And we can go forward, and we go forward quite a bit. That one student I showed in there, Brooke, she's doing that exact thing, looking forward to see how the trees will grow from now until the year 2100, based on, she takes 5 different scenarios of models, and she gets an idea of how they'll roughly grow in all areas of Saskatchewan. And so we can go forward if we can find some kind of relationship like climate to do that. We can also go forward in things like chemistry. If we can say, if you give the environment this much, let's say manganese, we know we're going to get a point where they can no longer take it up, and you're going to turn from an element that we need to an element that makes you sick. And we can measure that amount of manganese. And when you hit that threshold, we know you're going to make the force sick. And so those are the kinds of things we can go forward. We can look into the past to inform the future and say, wow, if you continue to do it, what you're doing, you're going to kill this many trees, or you're going to create a plume this high. We know your plume will travel at least 80 kilometers with this kind of density of effluent, and that effluent is going to carry about this much manganese. So after 5 or 6 years of slowly bringing that into the environment, you're going to start to make that environment sick, and we'll start to see the needles of conifers change. And those are the kinds of ways that we can go into the future. You're welcome.
That kind of sounds to me like there's an opportunity there for, from an education standpoint, to really bring in some math curriculum outcomes. Reading graphs and using that for predictive purposes.
Absolutely. We used to run, I used to teach a weather and climate class, and in my weather and climate class, we would make up scenarios of a tall smokestack coming off of a tire factory, and out would come effluent. And how far would that plume carry you? It's just a mathematical formula. If the wind is blowing this much, it'll carry the effluent this far in this direction. And so those are the kinds of things that you follow a simple formula, and you put in different changes of wind speed to see what happens, or wind direction. If you want to do, the dominant wind direction in winter is this direction, and what's the concentration of an element in a certain area, and how far will it go? So all those kinds of math problems are all out there, and the formulas are out there, and we simply adapted them to a weather and climate class. But you can do that with any kind of group. As we saw in our tree program, we can kind of take and make the math for any level that they're comfortable with, whether you're calculating the height of a tree using, tan, or inverse tan or something, or if you're just saying how high a tree is by measuring a distance and adding an angle or something like that. So these are the kinds of things, and you can adapt that to any level of math or calculus that you want to take it to.
Cool.
Yeah.
Are there some other questions? Is Brooke at a point where we could consider approaching her to do a seminar?
Potentially. I mean, she is a busy woman. She does have a job, but yeah, she's at the point. Her final draft is in now, and so her committee has signed off on it. And now we're waiting for her. Probably in late August, she'll have her defense. So once she's defended and she's Brooke with an MSc after her name, she probably feel a little more comfortable talking. But yeah, that's what she does. Trees in Saskatchewan going forward, right, into time.
Yeah, because she's also been a mentor for students on Beamlines.
Yeah, she has. Again, all my students get something from them. Zach, who's going to be a speaker in your series coming up, again, started out as a volunteer, and then he took my class, and then he ended up being one of my master's students. And again, Zach's about to finish. He's got his thesis out with his committee now, so he's coming to that point too, and for sure. Jay, Magali, Hafa, almost all of my students have either helped your students come in or else gone off and been their own mentors. Usually master's and PhD students were mentors, but my undergraduates are helping a lot of the students, like going into the chemistry labs and going into the muffle furnace labs, and those are the kind of things. So even my upper year summer students, who are my part-time students that are there, they're in and helping the groups too, because again, although they might get paid for it a little bit, they also get a lot out of it because they're meeting these students, and they get cornered and say, what's it like being a university student? What's it like coming from high school to first year? So there's a really nice kind of transition that, a professor can talk to them about that, or their parents can talk to them about that. But when you talk to someone who's 2 years older than you and they're asking, what's it like? It's a really nice kind of transition and a passing of that torch from what's it like to be a science student in environmental science.
Joe mentioned in the chat that Brooke was the mentor for one of his.
Oh, okay.
So that's a neat connection there.
Yeah.
Well, that's really, really good. Thank you so much for your time, Colin, and for being our first kick at the cat here. And thank you, everyone, for giving us your time today. I really appreciate it. And with that, I think we can probably sign off.
Okay, you're welcome.